We'll start by understanding sequences. A sequence is a function that computes an ordered list. For example, on average, Americans are eating around 25 pounds of cheese per year. The function f of n equals 25n generates the terms of the sequence 25, 50, 75, 100, etc. for n equals 1, 2, 3, 4, 5, 6. So by replacing n with these values, we end up with the terms of this sequence. This function represents the pounds of cheese consumed by the average American after n years. In this example, the domain of f of n is the set of natural numbers, which is also known as n, and the range is the set of multiples of 25. That is, here's the domain, the set of natural numbers, including 1, 2, 3, 4, etc. And the range is basically the set of the outputs is going to be all the multiples of 25, the positive multiples of 25. Sequences may be finite or infinite. A finite sequence has a finite domain, which is a subset of n, the set of natural numbers. For example, if I define f of n to be 7n for n being values 1 through 10, then the domain is just the natural numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and the range is these multiples of 7, which start at 7 and end at 70. An infinite sequence has the entire set of natural numbers at its domain. For example, if I define the same function, f of n equals 7n, but this time I define it for n belonging to n, the domain is going to be the set of natural numbers, and the range is going to be all the positive multiples of 7. A few notes on notation. Even though sequences are functions, we usually represent them using the nth term of the sequence, called an, instead of using the f of n notation, while x is the letter that we commonly use for the input of a function. We use the letter n for the input of a function that's defining a sequence, given that the inputs are natural numbers. Here's a typically named sequence. Normally we start with, like, say, a1, that means the first term of the sequence, a2, a3, etc., all the way to an, and we read these, as I said, there's no need to say a sub 1, a sub 2, a sub 3. No, you just say a1, a2, a3. That nobody is going to mistake that for you saying, for example, a squared, because if you were going to say a squared, you would have said a squared, or you would have said a to the power of 2. So when you just say a2, everyone should understand that you're talking about a subscript 2. And an, which is read as an, is the nth term of the sequence. It's also called the general term. Once we get a definition for a sequence, such as the last one was an equals 7n, then we can write a clearly defined definition for a given sequence. A note about the domain and range. Notice that with a function such as f of x equals 3x, the domain would be all real numbers, right? And the range would be all real numbers as well, because all y values would be involved in graphing this function, right? Would be outputs of this function eventually. Now, when you write it as a sequence, notice that you would have the domain being the set of natural numbers, so the inputs would start here at 1, but you wouldn't have any fractional or decimal numbers, only perfect whole numbers, or as positive whole numbers as the inputs. So here the range would be 3n, such that n belongs to n, right? So notice that these graphs for like functions like f of x equals 3x are continuous functions, right? And we can say that the domains are continuous set of data as well, right? But not with these. With these, the domain and range are both discrete set of data or set of numbers, right? So you can see gaps. These are not a continuous connected piece of a graph. All right, so here's a very typical way you may see a sequence defined. an equals n plus 3 over n plus 4 for n belonging to n. And here we're asked to find the first 5 terms of this sequence. And notice that because there's no restriction on n being just a part of the natural numbers, it belongs to the entire set of natural numbers. This is an infinite sequence, so there's no way you could actually list all the terms, right? You can only list like a finite number because you have a finite amount of time, right? So here we have, we'll just say a1 is going to be, just plug in 1 for n, so 1 plus 3 over 1 plus 4. So we get 4 over 5. That's the first term, right? a2 would be 2 plus 3 over 2 plus 4. So it would be 5 6. a3 would be 3 plus 3 over 3 plus 4, which would be 6 7. You're probably noticing a pattern here, right? So you probably have guessed the next term should be what? 7 8. Yeah, but that's because it's just going to be 4 plus 3 over 4 plus 4. And the last one, a5, or the fifth term, is going to be 5 plus 3 over 5 plus 4. So it'll be 8 9. Okay, and that's how you would find those 5 terms. All right, so for this next one, we want to find the first 5 terms as well. Notice that an equals quantity negative 1 to the n. So a1 would be quantity negative 1 to the 1, which is just what? Negative 1, right? a2 would be quantity negative 1 to the power of 2. You know that's going to turn out to be positive 1. a3 would be quantity negative 1 cubed, which is negative 1. You know negative 1 raised to an odd power always generates a negative 1. So a4, that's easy too, because we know that negative 1 raised to an even power is always going to generate 1. And a5 will be negative 1 to the 5, which is negative 1. So if we want to write them out, we'll say negative 1, 1, negative 1, 1, negative 1. You see, because of this, and then we just put 3 dots, meaning this pattern continues. Because of this continuous change in sign, this is sometimes referred to as an alternating sequence, okay? All right, here it says find the first 4 terms of this given sequence. And when the value of n is not specified, like in this case, assume that n belongs to n, meaning that the domain is all natural numbers. All right, so a1, that's just going to be quantity 1/3 to the 1 times 4 times 1 minus 3, right? It's just like functional evaluation, because after all, these are what? These are functions, right? So the main difference being that the inputs are very specific. They're natural numbers, right? So we get, let me just keep going up there. So we get 1/3 times 4 minus 3, which is 1. So we just get 1/3, right? For a2, we're going to have quantity 1/3 squared times 4 times 2 minus 3. So we get 1/9 times 8 minus 3, which is 5. So we end up with 5/9. And for the third term, we have quantity 1/3 cubed times quantity 4 times 3, minus 3, so we get 1 over 27 times 12 minus 3, which is 9. So we end up with 9 over 27, which is 1/3. For the fourth term, we end up with 1/3 to the power of 4 times 4 times 4 minus 3, which is 1 over 81. 1 to the 4 is 1, 3 to the 4 is 81, times 16 minus 3, which is 13. So we end up with 13 over 81. So if we wanted to write it, we would just say 1/3, 5/9, 1/3, 13 over 81, etc. Okay, that's how you would handle that one. All right, next we want to find the first 5 terms of this sequence. So you should be able to do this by now. Go ahead and see what you get before you continue in the video. All right, so A1 is going to be quantity -1 to the 1 times -2 times 1. Remember, we're just substituting 1 wherever we see n. So we get -1 times -2, which is 2, right? A2 is going to be quantity -1 squared times -2 times 2. So that's going to be 1 times -4, which is -4. A3 is going to be quantity -1 cubed times -2 times 3, right? So you get -1 times -6, which is going to be +6. A4 is going to be quantity -1 to the 4 times quantity -2 times 4. So it's going to be 1 times -8, which is -8. A5 is going to be -1 to the 5 times -2 times 5. So it's -1 times -10, which gives you 10. Now you can see a pattern here, right? Alternating sign, even numbers, right? So we want to write it out. We would say 2, -4, 6, -8, 10. So this is how you would go about generating alternating sign, even numbers, for instance, right? Okay, that's how you do that one. Let's just do one more of these. So the first 4 terms, right? See what you get and see if our answers agree. Pause the video. All right, so A1 is 5 times 1 minus 3 over 1 squared plus 1. So that's going to be 5 minus 3, which is 2, over 1 plus 1, which is 2. So we get 1, right? A2 is going to be 5 times 2 minus 3 over 2 squared plus 1. So that's going to be 10 minus 3, which is 7, over 4 plus 1, which is 5. A3 is going to be 5 times 3 minus 3 over 3 squared plus 1. So 15 minus 3, that's 12, over 9 plus 1 is 10. We'll go ahead and reduce it to 6 over 5. And A4 is going to be 5 times 4 minus 3 over 4 squared plus 1. So it's going to be 20 minus 3, which is 17, over 16 plus 1, which is also 17. So we get 1. So we can write it out as 1 7/5, 6/5, 1, and then we can put dots for continuation. All right, that's how you do that one. All right, next we want to see what we mean by convergent sequences. If the terms of an infinite sequence get closer and closer to a real constant, the sequence is set to converge to that number, and hence called a convergent sequence. For example, note how the terms of the sequence an equals 1 over n, they approach 0 as n approaches infinity. So, you know, we have 1 over 1, 1 over 2, 1 over 3. We skip over some, then we get 1/10, 100, just because these are really easy to compute, right? So notice the values are really approaching what? Smaller and smaller values until they get to 0. You're never going to go, you know, even get to 0, but you're going to get as close to 0 as you want to get. And that's called getting arbitrarily close to 0. And notice that it doesn't always have to be 0 that the magic number is, right? So if I look at, for example, 1 over n plus 1 instead, like this, the sequence an equals 1 over n plus 1, well, as n approaches infinity, that sequence wouldn't approach 0. It would approach what? 0 plus 1. So all these would get shifted up 1 unit. So, and the sequence itself would approach what? 1. All right, so that's what we mean by convergent sequences. Divergent sequences, on the other hand, do not converge to a real constant. For example, consider an equals n cubed. Notice the terms of this sequence are getting larger and larger without bound, right? Or if I just tweak it a little bit and look at f of an equals negative n cubed, then the terms would be decreasing without bound. However, it's extremely important to note that not all divergent sequences have terms that increase or decrease without bound. Here we have two sequences, neither of whose terms are increasing or decreasing without bound. Nevertheless, neither of them is also approaching a fixed number. So both of these would be considered divergent sequences, even though neither one has terms increasing or decreasing without bounds. Some sequences are what we call recursively defined. A sequence is said to be a recursively defined sequence if for every n greater than some bound b greater than or equal to 2, the values of Rn depend on at least some of the values of R1 through Rn minus 1. To translate that into plain English, it means at some point you start defining the terms based on terms that have already been known or occurred. So any terms of the sequence that are explicitly given are known as the initial conditions. Now we're going to look at the most famous recursively defined sequence of all, called the Fibonacci sequence. For the Fibonacci sequence, the initial conditions are the first two terms. Remember, the ones that are explicitly given. So f1 equals 1 and f2 equals 1. So in other words, the first two terms of this sequence are 1s. However, starting with 3 and onward, fn is going to be fn minus 2. That means 2 previous terms plus 1 previous term. So that means to get any term, we add the 2 previous terms. So look at the third element. That's going to be f3, right? So according to the definition, f3 is going to be fn minus 2. So 3 minus 2, that's f1 plus n minus 1, which is 2. So we get f1 plus f2. What would f4 be? f4 would be, plug in 4, so f4 minus 2, which is f2. And what is 4 minus 1? That's 3, so f3, etc. So to get any term starting with the third term, just add the 2 previous terms. So notice 2 is 1 plus 1. What's 3? The previous terms, 1 plus 2. 5, 2 plus 3, right? 8, 3 plus 5, etc. So this is what we call a recursively defined sequence. Here's another recursively defined sequence, and we're going to find the first 4 terms for it. Now, the initial condition given is that a1 equals 3. For n greater than 1, an is going to be negative 4 times an minus 1 plus 8. So the safest way to approach this is actually just use the formula. So a2 is going to be negative 4 times a2 minus 1, which is 1 plus 8. Don't skip this step because you're much less likely to make a mistake if you don't skip this step. So we end up with negative 4 times, what's a1? 3 plus 8. So that's going to be negative 12 plus 8, which is negative 4. Okay, so what is a3 going to be? Well, it's going to be negative 4a. Now we're substituting 3 for n, right? So 3 minus 1 is going to be 2 plus 8, right? So we get negative 4 times a2. We know what a2 is. a2 is negative 4 plus 8. So that's going to be negative positive 16 plus 8. So that is 24. Okay. So what about a4? Well, that's going to be negative 4 times a. 4 minus 1 is 3. So a3 plus 8. So it's going to be negative 4 times, we know what a3 is. It's 24. And then plus 8. Now we'll just go ahead and calculate that. So negative 4 times 24 plus 8, negative 88. And we're done. We were only asked to find the first 4. The first one was already given. So basically we're looking at 3, negative 4, 24, negative 88 for the answers. Okay, that's how you do those. All right, see what you come up with for this one before you continue the video. Okay, it's another recursively defined sequence. The initial conditions are given. a1 is 4 and a2 is 4. Then every term after the second one is defined by this expression. So little typo here, that should be k greater than. Let me fix it quickly. No, I changed my mind actually. It's not, because if I plug in 2 here, I get the third term. So we're good. The restriction here is fine. Okay, let's go on and find them. So a1 is 4. a2 is 4. So now I want a3. So that means I would want to use k equals 2 here. So I get a3, which is a2 plus 1, is going to be, so let me actually write it out like that so you can see it, which is going to be a2 plus a2 minus 1. Remember, I'm using k equals 2. So 2 minus 1 is 1, so I get a1. So I'm just going to add a1 and a2 to get my a3. So what is that? 4 plus 4, which is 8. So for a4, remember, that's going to be a3 plus 1, right? So I'm using k equals 3. So it's going to be a3 plus a3 minus 1, which is what? 2. Does this look familiar to you? Yes, it's in fact some variation of the Fibonacci, right? So if you were thinking that, you were correct. So what is a3? a3 is given as 8. We found it in the previous step. And what is a2? That's one of the initial conditions. It's 4. So what is it? 12. And that's all we had to do. Find the third and fourth term. Because the whole idea is understanding what's going on, not to overkill, right? Try this one, see what you get, and then come join me again. All right, a1 equals 3, an is n times an minus 1 for n greater than 1. So if I want a2, I'm going to have to go to the formula because this is the only initial condition. So a2 is going to be n, which is 2, times an minus 1, which is 2 minus 1. So that's 2a1, right? So it's 2 times, what's a1? 3, so that's going to give me 6. What about a3? a3 is going to be plugging in 3 now. 3 times a3 minus 1. 3 times a3 minus 1. What is 3 minus 1? That's 2. So it's 3a2. So I want 3 times, now I know what a2 is. We just figured it out. It's 6. So, and what is a4? Because we want the first 4 terms, right? So it's going to be 4 times a4 minus 1. So that's 4 a3. I know what a3 is. It's 18. So it's 4 times 18, which is 72. So basically we're looking at 3 for the first term, 6, 18, and then 72 for the fourth term. Okay, and we only have to find the first 4. Okay, all right, next we want to look at what a series is. A finite series is the sum of a finite number of the terms in a sequence. We can use the terms of the sequence to create a series. For example, consider the sequence given by this expression. an equals quantity 1/2 to the n. What are the first 4 terms of this sequence? Well, there'll be 1/2, and then square 1/2 to get 1/4, and then cube it to get 1/8, and then raise it to the 4th power to get 1/16. The sum of the first 4 terms of this sequence can now be written. Basically, we just write 1/2 plus 1/4 plus 1/8 plus 1/16. So when you see the word series, think what? Sum. That's all. So we usually represent this sum using what is known as summation notation, which utilizes the capital Greek letter sigma, shown here. For this particular sum, we would write this. We would the way you would read this as follow: the sum from I equals 1 to 4 of ai. This I here is called the index of summation, right? Or the summation index. So that means the sum from I equals 1 to 4 of, remember our sequence is 1/2 to the n, so we just write 1/2 to the I. And now we just run through the values of I, right? So first go with I equals 1, so that gives you 1/2 to the 1. Then you go I equals 2, so that gives you 1/2 squared, which is 1/4, plus I equals 3 will give you 1/2 cubed, which is 1/8, and finally I equals 4 would give you 1/2 to the 4th, which is 1/16. And then you can just go ahead and compute them by finding a common denominator and adding the fractions. You'll end up with 15/16. So this is called summation notation. The I is the index of notation, index of summation, sorry, or summation index, either way. Now, if we find the sum of the terms of a finite sequence, or find the sum of a finite number of terms of an infinite sequence, in either case, so we may deal with just a finite sequence, or we may just pick a finite number of terms from an infinite sequence. In either way, when we look at such a sum of a finite number of terms, we call the associated series a finite series, and we denote it using the notation capital S and then subscript n, so Sn. That is, when we say Sn, we mean the sum from I equals 1 to n of ai. So that means just run through the values of I, right? So starting with 1, so we get a1, and then go to a2, and then plus a3, plus all the way to what? To this top limit, so to an. We refer to the I, as I mentioned before in the summation notation, as the summation index or index of summation. And note that the summation index does not always have to start at 1. For example, you may find this kind of a sum that you're interested in, the sum from I equals 1 to 3 to 7 of AI. And even though I is the most common summation index, J and K are sometimes used, or you may use any other letter that you want, but the most commonly used are I, J, and K. We find the sum of an infinite number of terms of an infinite sequence. Then we're dealing with what I mean is, if we find the sum of an infinite number of terms of an infinite sequence, then we refer to the sum as an infinite series, and we denote it by S infinity, or sometimes simply just S. So if we don't have a subscript, that usually means we have a sum that is referring to the sum of the terms of an entire infinite series. So we represent it like this: S equals S infinity, which is the sum from I equals 1 to infinity of AI, which just means A1 plus A2 plus A3 plus continue forever. Okay, that's what that sum means, which we refer to as an infinite series. Let's go ahead and compute this finite sum. It's just from I equals 1 to 3 of quantity I plus 1 to the I. So remember, we're just going to run through the index values. So starting with 1. So we just get equals, instead of I, we're going to substitute 1, right? So 1 plus 1 to the power of 1, right? Plus, next comes the value I equals 2 plugged in here and then added, right? So now we have I, we're going to replace it with 2, so 2 plus 1 to the power of 2. Next, we go to 3, so quantity 3 plus 1 to the power of 3. And that's it. We only had to run through from values of I from 1 to 3. So we get 2 plus 3 squared, which is 9, plus 3 and 1 is 4 cubed, which is 64. So now we add those. So basically 11 and 64, so 75. That would be the sum we're looking for, okay? Try this one and see what you get before you continue the video. All right, so we're going to run through from values of K, which is the summation index here, from 1 through 4, and add, right? So we start with 1, K equals 1, so we get quantity negative 1 to the power of 1 times 1 plus. Now we use K equals 2. So wherever we see K in this expression, we're going to replace it with 2. So we get quantity negative 1 squared times 2. Both instances of K were replaced with 2. Now we do the same thing for 3. So plus quantity negative 1 to the 3 times 3. And lastly, we use 4. So quantity negative 1 to the 4 times 4. So we end up with negative 1 to the 1, which is negative 1 times 1, so negative 1, plus, now this is going to be 1 times 2, so just 2, plus this is going to be negative 1 times 3, so negative 3, and this is going to be 1 times 4, so just 4. So you get negative 1 plus 2 minus 3 plus 4, right? So that's 1 minus 3 is negative 2 plus 4 is 2. And that's how you would go ahead and take care of that. And by the way, if you just look at that itself, notice it's a nice way of generating what? Alternating positive and negative number integers, right? All right, go ahead and try this one and then join me again. Okay, so this time we gotta be careful. The index is starting at 2. So the first term that we're gonna be adding is going to be quantity 18 minus 9 times 2, right? And then we want to use I equals, so the values of I we're going to run through are right here. I equals 2, I equals 3, I equals 4, and I equals 5. So now we're going to move on to 3, so we get plus quantity 18 minus 9 times 3, and then plus quantity 18 minus 9 times 4. Finally, plus quantity 18 minus 9 times 5. We're going to learn about some properties soon that will make handling some of these easier, okay? But for the time being, we're just getting practice with the basics. So this is going to be 18 minus 18, right? Plus this is going to be 18 minus 27, plus this is going to be 18 minus 36, and finally plus 18 minus 45. So we end up with 0 plus negative 9 plus negative 18 plus, let's see, 8 from 15 is 7, 1 from 3 is 2. So negative 27. So we end up with basically negative 9 minus 18 minus 27. That's basically negative 27 minus 27. So negative 27 times 2, or negative 54. All right, so that's how you would do that one. Remember, sometimes I does not begin at 1. Try this one and be careful with your values of I. It's a good idea to write down what I values you're going to run through, okay? So do that before you start. All right, we're going to run through the values of I from negative 1 to 5. So the values are going to be negative 1, 0, 1, 2, 3, 4, and 5. Okay? So start with negative 1. So we get quantity negative 1 squared plus 9 times negative 1 plus quantity 0 squared, we're using 0 now, plus 9 times 0 plus, I should have started a little bit further left. Let me do that. That's one good thing about these whiteboards. No, give me a minute. All right, there it is, just like magic. All right, and then now we're at value 1, right? We ran through negative 1 and 0. Now we're going to 1, so we get quantity 1 squared plus 9 times 1. Now we're at 2, so we get quantity 2 squared plus 9 times 2 plus quantity 3 squared plus 9 times 3 plus quantity 4 squared plus 9 times 4, and lastly quantity 5 squared plus 9 times 5. All right, so carefully, right here we have 1 minus 9, right? So 1 minus 9 plus, try to not to do too much in your head. That's where mistakes happen, right? And then that's just going to be 0. Next, we're going to have 1 plus 9. That's simple enough. I'm just going to put 10. Plus, that's going to be 4 plus 18, right? So 22. Here we have 9 plus 27. I'm just going to write it down. And then we have 16 plus 36. And then we have 25 plus 45. All right, so that's going to be negative 8 plus 10 plus 22 plus 9 plus 27 plus 16 plus 36 plus 25 and 45, that's 70, right? So now we're just going to compute that. I can try to do a little bit of the sums to make it a little bit easier to type into a calculator, right? So that's going to be 32 minus 8. So actually, negative 8 and 10 is 2 plus 22 is 24. These two are going to give me 36, right? And 16 plus 16 plus 36 plus 70. All right, so that should be good enough. We'll go ahead and figure it out now. So 24 plus 36 plus 16 plus 36 plus 70. So 182 is the value of that sum. Okay, so very easy. Just have to be patient and careful. All right, this next step is going to have some subscripts involved. So it looks more difficult, but it's not. Here's what we're going to do. We're going to run through the values of the index from 1 to 5 first and keep the x, right? So we get what? So we get, remember, the values of I we're going to run through are 1, 2, 3, 4, 5. So starting with 1, I get negative 5x, and I'm just going to put the subscript 1, just like that, plus 9, right? Plus quantity negative 5x, run through the value of 2, so x2 plus 9, and then plus quantity negative 5x3 plus 9 plus quantity negative 5x4 plus 9, and lastly plus quantity negative 5x5 plus 9. All right, so now we plug in for what x values are. x1 is negative 2, so I'm just going to replace x1 with negative 2. So negative 5 times negative 2 plus 9 plus, I'm going to have negative 5 times x2, which is negative 1, plus 9 plus negative 5 times x3, which is 0, plus 9, plus negative 5 times x4, which is 1, plus 9, and then finally negative 5 times x5, which is 2. So I end up with 10 plus 9, and this is going to be plus 5 plus 9, that's 0, so plus 9, that's negative 5, so minus 5, and then plus 9, and then that's going to be net minus 10 plus 9. Now from these 9s, I think you can see one of the properties that are going to come up later. When you have the sum from I equal 1 to 5 of 9, you see what that's going to be? 1, 2, 3, 4, 5. It's just going to be 9 times 5. You see? So that's going to be one of the rules we're going to learn later. So I noticed there's a lot of cancellation here going on. So, well, sum 10 and negative 10, right? 5 and negative 5. That just leaves me a bunch of 9s, doesn't it? 1, 2, 3, 4, 5, and they're all positive. So 9 times 5 is what? 45. And that's all there is to that. So don't let the index on the X scare you. It's very simple. All right, let's go ahead and move on to another. Notice that sometimes they'll ask you to specify what each of the terms are. In that case, just keep them separate like this and just write down what each of those sums are first, right? So for example, for this, you would say what? 10 and 9, you would say 19 is the first one. And then here you would have what? 5 plus 9, which is 14, right? And for the next one, you would say 0 plus 9 is 9 is the third one. Here you would say negative 5 plus 9 is 4, etc., right? The last one would be what? Negative 5 times 2 is negative 10 plus 9 is negative 1. And then you can just add those. You'll get the same thing. Okay? There we go. All right, the next thing we want to do is learn about some summation properties and then some summation rules. So let's go ahead and start with properties. All right, here's one I've been hinting at for a while, that if you have the sum from I equals 1 to n of just a constant, which has no I associated with it, then it's just going to be n times that constant. Here's the proof. The sum from I equal 1 to n of c, that's just going to mean what? C plus C plus C. How many times? N times, right? So what is n terms of C? Well, that's just going to be n times C, right? Like for example, if you have 2 plus 2 plus 2 plus 2 plus 2, that's how many what? That's 5 2's. So how can you figure that out? You can just go 5 times 2. That's the definition of multiplication, isn't it? That's all we're talking about here. Like that, okay? For summation property 2, we want to talk about what happens if you're doing a sum and you have a constant multiple, right? So here AI is going to be the varying term and you have a constant times it. Well, as it turns out, you can pull the constant out of the summation and just deal with the summation, then multiply the constant by it. Here's the proof of why that works. You know, see if you can come up with the proof on your own now that you kind of know what is going on. If not, watch this and definitely try the next one on your own. So here we have the sum from I equal 1 to n of CAI, right? That means what? Well, run through the values of I, right? So CA1 plus CA2 plus CA3 all the way to what? CAN. Now go ahead and factor out a C. That leaves you what? A1 plus A2 plus A3 plus AN, etc. Well, what is that? What is this sum? That's the sum from I equals 1 to n of AI, right? That's why you get C times the sum. So the summation of a constant times a particular term is just going to be the constant times the sum. And that's QED. That means that's finished. The proof is finished. Remember, quod erat demonstrandum, Latin for that which was to be shown. Okay, let's move on. All right, so the third property we're going to look at says, look, the sum of basically a sum is going to be the sum of the two sums. So sum of AI plus BI means is equal to the sum of from I equals 1 to n of AI plus the sum from I equal 1 to n of BI. Let's see why that's true. Try to prove this on your own before you watch the rest of the video. All right, so what does the sum from I equal 1 to n of AI plus BI mean? Well, just run through the index, right? So plug in 1, so you get A1 plus B1. Then plug in 2, so you get what? A2 plus B2. Then plug in 3, so you get A3 plus B3. And then dot, 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 continue the pattern until you plug in what? The upper limit, so AN plus BN. Now look, I can, because it's a sum, I can use associative and commutative properties to put all the A's next to each other and then put all the B's next to each other like that, right? So what is this? Well, that's the sum from I equal 1 to n of AI. And what is this? The sum from I equal 1 to n of BI. And that's it. we've proved it. That's what we were trying to prove, right? See, very nice, simple proofs, but gives you a good feel for how pure mathematics is done, okay? Next, we want to prove the same rule for a difference. If you didn't do the last one, definitely do this on your own before you continue, okay? So we want to show that the sum of AI minus BI is going to be the same as the sum of AI minus the sum of BI. So again, just run through the index, right, for the proof. We start with the left side and we end up with the right side. That's a classic proof strategy. You know, it's not the only proof strategy, but it's one that often works and we utilize it quite a bit. When you're trying to prove some kind of an equation, you start with one side of the equation and somehow end up with the other side until you prove it and you finish it. But of course, you want to do so through some correct and mathematically supported steps. Now we're going to run through the values of I on the left side. So we get A1 minus B1 plus A2 minus B2, etc., all the way up to AN plus BN. Now we're going to add basically all the A's together. And remember, the B's are all going to have a negative on them, right? So we can factor out a negative and then add all the B's as well, right? So notice we just end up with sum of AI minus sum of BI, which is what we were supposed to prove. We started with the left side, we ended with the right side, therefore QED, okay? Next, we want to look at 3 summation rules. Summation rule 1 has to do with the sum from I equal to n, 1 to n of just I, right? Well, that means 1 plus 2 plus 3, etc., all the way up to n. And that is given by n times n plus 1 over 2. The sum from I equal 1 to n of I squared, that means 1 squared plus 2 squared plus etc., all the way up to n squared. So the sum of the first n square natural numbers, basically, right? That turns out to be n times n plus 1 times 2n plus 1 over 6. And for I cube, which is basically 1 cube plus 2 cube, so the sum of the first n perfect cubes, right? That turns out to be n squared times quantity n plus 1 squared over 4. Now, we will prove rule number 1, but the second and third one are going to be proven after you learn more about summation in future classes if you continue with more advanced math courses, because they're going to require some things that are going to be a little bit beyond our class. But we can apply all 3 of the rules to make computing summations an easier task. So while we won't prove the second and third, we will basically use them. So just take my words that they are true. Here's the summation rule 1 that we're going to prove. And the strategy is basically the same strategy that a young Carl Friedrich Gauss impressed one of his teachers with, because basically one day the teacher went in and had some was thing to take care of. He wanted to sit there and do some of his own work. And so he said, what am I going to do? I'll just tell him to add the first 100 natural numbers, So he said, here, just sit there and do 1 plus 2 plus 3. He figured that was going to keep the students busy for some time, right? Well, Gauss answered it almost immediately, okay? Because he basically used this kind of a strategy, which is, of course, a lot easier for just 1 to 100. But this is what he did. He basically write the series once this way, 1 plus 2 plus 3 plus etc. up to n, and then turn it around, write it backwards, right? N, and then n minus 1, and then n minus 2, and then n minus etc., all the way till you get to 3, 2, 1, right? Notice that now if you look at down like this, each of these is just going to be n plus 1. So n plus 1, and then this, what's 3 plus n minus 2? That's n plus 1. He realized you end up with n of these terms that are being added. So if I add these two expressions, I get 2sn equals these, which are nothing but n of these n plus 1s. So to get the sum, all we have to do is divide both sides of this equation. If I just rewrite this again here, 2Sn, just divide two sides of this equation by 2, and you end up with Sn equals n times n plus 1 over 2. Notice Gauss did it for 1 to 100 like this: 1 plus 2 plus 3 plus dot 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 plus 98 plus 99 plus 100, right? And then he wrote the 100 here, and then the 99, and then the 98, and then dot dot dot, and then plus 3 plus 2 plus 1. Then notice you get 101 plus 101 plus 101, right? Plus 101. So this was a brilliant method that he used, and he realized there's 100 of those 101s, but that's, look, that's S100 and S100. So 2 times S100, if I add the 2, is going to be this. So 2 times S100 is equal to 100 of the 101s. So what is the sum of the first 100 natural numbers? 100 times 101 over 2. You can imagine that the teacher was not very pleased. Well, with the fact that he couldn't get his work done, but I'm sure he was quite impressed by young Gauss, Gauss, very, very famous mathematician. So here's a summary of what we just learned. The properties were thus that the sum from I equals 1 to n of a constant is just the n times the constant. The sum from I equal 1 to n of a constant times ai is just going to be c times the sum from I equal 1 to n of ai. The sum from I equal 1 to n of ai plus bi is going to be this, the sum of the two sums, right? And I think I repeated this. I meant difference here. Let me fix that. All right, that's better. So we meant the sum from I equal 1 to n of ai minus bi equals the sum of ai minus the sum of bi. For the properties, we learned that the sum from I equal 1 to n of I is going to be n times n plus 1 over 2. For I squared, it's going to be this, and for I cubed, that. All right, let's go ahead and apply these. I have them here to remind you of what we're going to use. So notice here we want the sum from I equals 1 to 100 of 17. Notice that is just going to be, here we're missing our I here. I equals 1 to 17 to 100 of 17. So as you know from this rule, it's just going to be 100 times 17. And of course, more importantly, you should know why that is true, because we proved it, right? Okay, so that's simple. That's how you do that. Try this one. See if you can get it on your own. Here are the rules. See which one you should use, or which ones you may use more than one, and then see what happens. All right, so I noticed that there's a constant multiple here first and foremost, so I'm going to go ahead and take it out. So I know this is going to be the same as 5 times the sum from I equals 1 to 7 of I squared. And now I also realize that this part I can use the square rule for, right? So it's going to be n times n plus 1 times 2n plus 1 over 6. My n here, of course, is what? Is 7. So I'm going to get times 7 times 7 plus 1 times 2 times 7 plus 1 over 6. Now I just need to compute that. Let me simplify it a little bit before I plug it into the calculator. So it's going to be 5 times 7 times 8, which is 56. And then 14 plus 1 is 15. and then that over 6. Now I'm going to plug it into a calculator. So we have 5 times 56 times 15 divided by 6. We end up with 700. All right, so that we use two of the properties. Remember, we use this property, but we use the property and a rule, right? So we use this property and we use this rule, okay? That's all there is to it. All right, try this one. You should definitely be able to do this one now that you saw the last one, okay? So do your best to do it on your own first. Okay, so I noticed that I can firstly, using a combination of two properties, go ahead and separate these, right? So I'm going to do that using a combination of these two rules. I'm going to separate them, so I get equals the sum from I equals 1 to 6 of 4i squared I can't even go with minus the sum from I equals 1 to 6 of 5i plus the sum from I equals 1 to 6 of 7. Now I'm going to go ahead and apply the constant multiple rule to bring the 4 and the 5 out. So we get 4 times the sum from I equals 1 to 6 of I squared minus 5 times the sum from I equals 1 to 6 of I plus the sum from I equals 1 to 6 of 7. So now we're ready to go ahead and apply the rules and the properties. So for the first one, we're going to have 4 times this sum, and for this we're going to use this formula again. So that's, and now remember we're using n equals 6, right? So 6 times 6 plus 1 times 2 times 6, which is 12 plus 1 over 6, minus 5 times the sum for I is just n times n plus 1 over 2, and remember n is 6, so 6 times 6 plus 1 over 2, and then plus, for this one we're just using the simplest rule, the sum from I equals 1 to n of a constant, so it's just going to be the constant times 7, so 6 times 7. Alright, so let's simplify it a little bit. So it's going to be 4 times 6 times 7 times 13 over 6 minus 5 times 6 times 7 over 2 plus 42, right? So notice that we can cancel out the 6's here, and 2 and 6 leave us 3 here. So we have 28 times 13 minus 15 times 7 plus 42. So now we're just going to plug it into a calculator. So 28 times 13 minus 15 times 7 plus 42. 301. All right, so that's just the use of several of these properties and rules together, and that's how you do that one, okay? All right, here's one last one to give you plenty of property, practice property. Well, some kind of property, right? Mental property. All right, so make sure you try this on your own first before you rejoin the video. Okay, so very simple, right? We're just using these three rules. That's all we're doing. So just be careful. So for the first one, we're using the cube rule. So we're going to get n squared times quantity n plus 1 squared over 4, and n is what? 5. So we're going to get 5 squared times 5 plus 1 squared over 4. Now we're going to the squaring rule, right? This one with the squares. So 5 times 5 plus 1 times 10 plus 1. 5 times 2 is 10 plus 1 over 6. Plus, now we're doing the I rule. So 5 times 5 plus 1 over 2. Now, the simpler we make it, the easier it'll be to plug into the calculator. So I always like to do that. So 25 times 36. 5 plus 1 is 6 squared is 36 over 4 plus 5 times 6 times 11 over 6 plus 5 times 6 over 2. 4 and 36 give me 9 on top. 6's cancel out. 2 and 6 give me 3 on top. So 25 times 9 plus 5 times 11 is 55 plus 5 times 3 is 15. So that's all we have to punch into the calculator. So 25 times 9 plus 55 plus 15. 295. All right, so there's that, and summations are used all over the place as you go into more advanced mathematics. So you really want to be comfortable with them. Make sure you get plenty of practice, and take care until our next video. That should do it for this one. See you next time.